right, so let's kind of look at these three thermal variables a little bit. Delta S is entropy, which is a measure of disorder. Nature favors disorder, an increase in entropy. Delta H refers to heat energy, endothermic, exothermic, whether I have a positive or negative delta H. And then G is a measure of free energy, which lets us kind of like gauge the spontaneity of a reaction. If delta G is negative, the reaction tends to be spontaneous. There's a release of free energy. All three of these are considered state functions, which just means that they depend on the difference between final and initial conditions. So we've looked at that middle equation where we did heat of formation. We did total heat of formation of the products minus total heat of formation of the reactants, and we got the energy change for a chemical reaction. You can do the exact same thing with delta S and delta G. So for example, let's look at delta S down here. We want to calculate the change in entropy for this chemical reaction. So the numbers they give us are entropy values. We're going to set this up exactly the same way we did with heat of formation. Products minus reactants. And notice that this is per mole. So if I have more than a mole in the balanced equation, I need to multiply by the coefficient. So let's start with the products. My products. I'm going to have 2 times that sulfur dioxide, 248.0. I'm going to leave the unit out for now. I know it feels really naughty, but we'll get back to the unit in the end. Plus, let's see here, 2 times that nickel oxide, 38.0. Okay, so this was the nickel oxide, and this was my sulfur dioxide. Common mistake, people always forget that you got to start with the products minus the reactants. Here are my reactants, 2 times the nickel sulfide, 53.0. That's the nickel sulfide. And 3 times the oxygen. Notice that oxygen is not 0. Its heat of formation value is 0. It doesn't have any energy change for a pure element. But O2, diatomic oxygen gas, does have an entropy value. And in fact, it's kind of high. Notice the 2 gases have the higher entropy values. That makes sense. Gases are supposed to be more disordered. The 2 solids have pretty low entropy values. 53, 38, that makes sense. Solids have less disorder. They're more orderly. Okay, so it is going to be 3 times oxygen, 205.0. If it was heat of formation, oxygen gas diatomic would be 0. But it does have an entropy value, and it's very high, because oxygen and any gas would be disordered. That's the O2. All right, so we plug this all in our calculator. Super easy, plug and chug, and we get delta S. Delta S, I don't know, let's just say like negative 149. Okay, so there's the numerical value. Now we got to put the unit in with it. So let's just take a snapshot. Okay, so how about this guy? The 2. From the balanced equation, that means 2 moles. And then this entropy is the 248.0, and the unit is joules per Kelvin mole. Or sometimes it's mole Kelvin. Same thing, I guess. Okay, so look what happens to the unit then. I've got moles times joules divided by Kelvin times mole. Moles and moles cancel. So here's your final unit. Oh, cute. Joules per Kelvin. And there she is, my delta S. So you have to be a little careful because they will ask for units. Technically, that mole is going to cancel because the coefficients in the balanced equation do represent moles. And now again, we can kind of look at this and see if it makes any sense. Nature favors disorder. So we would normally favor an increase in entropy. This is a decrease in entropy. Does that make sense? A decrease in entropy means that the particles are becoming more orderly or less disordered. Now we could say that decrease in entropy means, I don't know, what's the best way of wording this? They're becoming less disordered. Does that make sense? If I look at the balanced equation, I've got 2 moles of solid on the reactant side, 2 moles of solid on the product side. But, I have 3 moles of gas on the reactant side and only 2 moles of gas on the product side. So I could look at this 2 different ways, and in both ways it makes sense. I have less total particles. I'm going from a total of 5 moles down to a total of 4 moles. And there's less moles of gas. So yeah, either way that kind of makes sense. That we should have a decrease in entropy. Okay, so watch what else we can do. So we could do this whole thing, this products minus reactants. We can do that with all 3 variables, delta S, delta H, delta G. We can also do Hess's law. We can do Hess's law with any of those variables. So we were looking at delta H before, like heat changes. You could also look at free energy changes. So if I have a 2-step reaction to form carbon dioxide, I want to manipulate these 2 little elementary steps and try to get the overall desired balanced equation. And again, like delta G would let me know if this is likely to be spontaneous. Negative delta G means there's a release of free energy, which is favorable in nature. So if this ends up being an overall delta G, then I know that that reaction is likely to be spontaneous. Okay, so let's see what we want. 2 carbon monoxide on the reactant side. And the only place that I see it is right here. So let's take this first one and flip it. We'll flip the whole thing. So now we got 2 carbon monoxide plus 4 waters. And I think water is always gas, so I don't need the phase there. Forming 2 methane and 3 oxygen, O2. So these will be my delta G values. And again, this little degree symbol, that just means that everything is in their standard states. So the oxygen is a gas, the methane is a gas, the carbon monoxide is a gas, and we're measuring this delta G with water in the vapor phase. That's all the little degree symbol means. So if I flip it, this becomes positive. Oh boy. And these would be in units of kilojoules. A positive delta G, that's not looking spontaneous. Okay, so what else do we want here? We want, okay, well I want 2 oxygen on the reactant side, but that's going to be a little messy because I got 3 oxygen on the product side. I don't know, let's skip it. I mean, if you get something where you're like, I don't know, there's oxygen in both of these elementary reactions, skip it and move on. I promise these things will work. Let's try to get the 2 carbon dioxide on the product side. Because I only see carbon dioxide in one place. It's in the second reaction, and it's listed as a product, which is where I want it. But I want 2 moles. So let's take that second half reaction, and we'll multiply the whole thing times 2. So we'll keep the 2 methane, 2 CH4, 2 CH4. This time I'll have, 4 oxygen. I'll produce the 2 carbon dioxides and 4 waters. Then I'm going to take that negative 801 and multiply by 2 for a negative 1602 kilojoules. Okay, let's see if this works. Oh, brother. Okay, I want this. I like that. I do not want these 4 waters, but thankfully they cancel. Excellent. I do not want these 2 methanes, but they also cancel. Oh, yes, this is perfect. I was kind of concerned about the oxygen. I want 1 oxygen. Well, here I'm going to produce 3. And then here I have 4. I can knock that down to 1. That's a 1. Well, that's a messy looking 1. There, 1. I want you. And then I have my 2 carbon dioxides. Excellent. I have the desired equation. So now all I have to do is add these to get my overall delta G. I would end up with a negative 514. Often with delta G, we're not so concerned with like the quantity as we are the sign. I have a negative delta G. This is likely to be spontaneous. So there, we can do a lot of those same calculations that we did earlier in Chapter 6. We can do those with any of these thermodynamics variables. Delta S, delta H, delta G. It's good stuff, isn't it?